Hello students, you should be able to hear me just fine, but basically what I figured I would do, it's Zoomless Wednesday after all, is I would go through how to do these advanced circuit problems with you. I had to go really fast in the Zoom today, today's Tuesday, and I'm going to slow things down just a little bit and hopefully this will make a little more sense to you. We're going to begin by looking at problem number 2 right here. Okay, so problem number 2. And understand, being able to explain these resistors in reference to each other is very important. So you should be able to look at this and say, okay, we have a 1 and a 2 ohm resistor, okay, and the 1 and the 2 ohm resistor are in series with one another, okay. You should also be able to look at this and say, all right, the 3 and the 7 ohm resistor are in series with one another. And then you should be able to say the top branch and the bottom branch are in parallel with one another, and each of those are in parallel with the battery. More on that in a second. So one thing that's always useful, got to start out by filling out the table. So I've already got the table pre-made for you, but we still need to write all our resistors in there. This Ohm's law table. Notice the units have already been written at the top of the table, so I do not need to rewrite ohms for each of those. That's covered by the units at the top. Beginning with our top branch, you guys can look at that and see that we have a 1 and a 2 ohm resistor. Now remember, I said they're in series with one another. What's our rule for series? If you don't know, you have an equation sheet that should have all the equations that you need to know. And the resistance for series, you just add them together. So this top branch is basically going to be 3 ohms. That's going to represent the entire top branch. Now on the bottom branch, I'm going to do the same thing. On the bottom, I have a 3 and a 7. Because they're in series with one another on that bottom branch, this is going to be equal to 10.0 ohms, or 10 ohms. Now, at this point, let me show you what we've done. You need to be able to understand what we're doing. When we simplify things, you need to be able to understand why we're doing it and what that actually means. So basically, we've simplified the circuit down to this, where we have a 3 ohm resistor in parallel with a 10 ohm resistor, and in parallel with a battery with a magnitude of 7.0 volts. That is crucial that you understand that. And so at this point, you should be able to look at that and say, oh, well, this is just like a parallel circuit problem that we've done before. You ought to be able to look at that and say, oh, well, 7 volts is the voltage drop across the battery, and because I'm in parallel, well, V total is equal to V1, which is equal to V2. You need to be able to understand that. And so within reason, then you could say, oh, well, if it's 7 volts, that's going to be 7.0 volts across the top branch, and that's going to be 7.0 volts across the bottom branch, okay? Because they're in parallel with one another. Now, understand this. For this problem, then, you do not need to find REQ. But because the instructions tell you to determine REQ for each circuit, we are going to go ahead and find REQ just because it's good practice. Now, at this point, like I just showed you, we have a 3 ohm, again, imaginary 3 ohm, and imaginary 10 ohm in parallel with the battery. So because they're in parallel, my rule for parallel resistance is as follows. 1 over REQ is equal to 1 over R1 plus 1 over R2. So in this case, I'm not going to say R1 and R2. Instead, I'm going to say, all right, we have a 3 ohm and we have a 10 ohm. Okay? And so then my REQ, I'm going to end up getting 1 over REQ is equal to, you have to forgive me, there it is. Here's my calculator. I got to do this in my I can't do it in my head. And you shouldn't either. Use a calculator. So I get 0.433. Now understand, that is not the answer. Okay? 0.433 is not the answer. That is part of the answer. Now, in order to finish this problem, I'm going to invert. That's a math term. I'm going to invert, which means flip both sides. Or you can just think of it as doing 0.4, that's really bad, 433 to the -1 power. It's the same thing. By doing that, I get a value of 2.31. That is going to be units of ohms, and that is the REQ. That's the REQ. So we're good. We're good to go. All right, so anyway, we did that just because that's what the question asked us to. It's not actually that useful. What is useful, though, is understanding these 7-volt values that I have up here. So if I have 7 volts across the top, that's great. But the thing is, the 1 and the 2 ohm resistor are in series with one another. Voltage isn't constant in series, but current is. If you don't believe me, you can look it up on your equation sheet. Again, you should have that equation sheet. In series, current is going to be equal to the current through every individual resistor. Now, we don't have current, but we do have voltage. So what I can say is, all right, I'm going to do 7.0 volts, and I'm going to divide that by 3.0 ohms. If you don't understand why, well, remember, our equation for VIR is like this, right? V equals I times R. And so if I'm looking for I, that's going to be equal to the voltage over the resistance. All right, so anyway, that's what we're doing here. When I do 7 divided by 3, I get 2.33. Now understand, that's 2.33 amps. All right, it's going to be 2.33 amps. Let me switch to, yeah, that's fine. And the thing is, if that's the total current through the top branch, that means this is also the current through this one, and that's also the current through this one. And the thing is, because those are both real resistors, 1 ohm, that's a real resistor. 2 ohm, that's a real resistor. I can actually put that information on the table, so I'll go ahead and do that. This is current, so it's going to go in the current column next to the relevant resistors that I just told you about. So 2.33 right there, right there. Next thing we're going to do, I see my face is in the way, is I'm going to do something similar for the bottom branch. Now again, I need current because 3 and 7 are in series with one another. So if I know current across the whole branch, I know current through each of those. But once again, I have 7 volts. I'm going to divide by 10 ohms, all right? And by doing that, I get a current of 0.7 amps. So if I have 0.7 amps through the whole branch, because these are in series, that means I'm going to have 0.7 amps here, and I'm going to have 0.7 amps here. And just like before, because the 3 and the 7 are real resistors, I'm going to put that information in my table. So that means I'm going to put 0.7 here, 0.7 here. All right? And remember, guys, I've told you before, if you've got 2 out of 3, you are good to go. As long as you got 2 out of 3 pieces of information, you are good to go. So I'll do 2.33 times 1. Math happens. You get 2.33. I do it again. I get 4.66. I do it again. I get 2.1. And I do it again, and I get 4.9. So again, I'm just using V. Look up here at the top of the table. V equals I times R. That's the reason we do the table this way. All right, so it helps you remember what mathematical, operation you have to do. So anyway, we've filled out the table. There are some checks you can do here. Because the 1 and the 2 are in series with one another, right? These are in series with one another. Then we ought to be able to add the voltages together to get the total voltage. In fact, if you do that, 2.33 plus 4.66 basically gives you 7 volts, which as we learned earlier, 7 volts is the current in the top branch. You can do the same thing with the next two. 3 and 7 are in series with one another. And so, if you look at your that branch, you add the two together, 2.1 and 4.9, what do you know? You get 7 volts again. So it all works out. Math works. Let's take a look at the next problem. All right, let's scroll down and look at number 3. So here's number 3. Now this one is a little more, a little more standard. That last one was kind of weird. This one is a little more of what you should expect. I'm going to go ahead and fill out my table. And typically when I fill out the table, I go in clockwise direction. Sorry, I did that the wrong way. I go clockwise around the circuit. So I got 1.5, I have a 3.0, I have a 0.5, and I have a 0.7. So I'm just putting everything where it needs to go. Now, as I've told you before, you look for the most specific part or the most complex part of the circuit. And what I see is 0.5 and 0.7. That's the most specific part, so I'm going to begin there. So I'm going to start with this group right here. Now notice, these are not in series with one another. They're in parallel with one another. And if you don't believe me, you can color code it. Remember, in color coding, if you have the same pressure drop If you have the same color difference across these two resistors, they're in parallel. And so my rule for parallel is that 1 over junk. So what I'm going to do over here, all right, is I'm going to say, well, 1 over 0.5 plus 1 over 0.7, and I'm going to go ahead and cheat and just show you guys basically what I'm doing in the calculator. I'm doing this to the -1 power, as should you. And I'm going to be really careful with my parentheses. Technically, like if I'm doing this, I'm going to do parentheses around each of these, and then a larger group of parentheses to do that -1 to. And it'll load up there in OneNote in a second. I'm going to go ahead and type it in the calculator. And as you're following along at home, which I encourage you to, because you should, you need to know how to do this, check this in your calculator. Make sure you're getting the same answer that I do. Now I got 0.292. So I'm going to write that right here, 0.292 ohms. And that's reasonable. Remember, a good way to make sure you did that correct is that your equivalent resistance in parallel should always be less than either of the two individually. And so 0.92, less than 0.5, less than 0.7, we're good to go. And so now at this point, basically, and I'm going to zoom out to show you kind of what we're talking about, basically we've just simplified this circuit so that we've got a 1.5 resistor, we've got a 3 ohm resistor, and now we have a ooh, that was an ugly symbol. 0.292 ohm resistor, and they're basically in series with the battery. And so because they're all in series, that makes finding REQ very easy. So the next thing I'm going to do is I'm going to say, well, REQ is equal to 1.5 ohm plus 3.0 ohm. They're all in series, so you just add them together. Plus this imaginary 0.292 ohm resistor. And I'm going to add them all up. I'm going to do that right now. And I get 4.792. Hope that's right. I don't remember these numbers. It's been a while. So anyway, there's my REQ for the whole circuit. Now, that by itself is not very useful, but it does enable us to use Ohm's law. Not just any Ohm's law. Ohm's law for the whole circuit. So here it is, V equals I times R. But if we're dealing with the whole circuit, we say, oh, V total equals I total times REQ. That's the whole thing. So what's V total? Voltage across the battery is 3.0 volts. I total is what we're looking for. And REQ is going to be 4.792 ohms. Always put units. And my face is in the way again. Get out of the way, face. There we go. All right, so 4.792 ohms, all right? So that's fantastic. Let's solve for I total. I'm going to do 3 divided by my resistance, and I get 0.626. And I am out of room, I think. I total equals 0.626. Does that show up on screen? Yeah. And it's going to be amps. Okay, always make sure you've got units that goes along with what we're talking about. Now, that is an important number. And guys, one thing I recommend that you do is whenever you get a number, go back and apply it. Basically, what we just solved for is we solved for the current through the battery. So what that means is that's 0.626 amps through the battery. Now, why do we care? Because in series, as you should know by now, I total is equal to I1 is equal to I2, blah, 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 blah. And so I'm going to apply that to every resistor that's in series with the battery. So that's going to be the 1.5, that's going to be the 3.0, and it's going to be this 0.626. I'm sorry, this 0.292 ohm resistor that we made up, okay? Now, for all the resistors that are real, okay, like the 1.5, that's a real resistor. I can plug that in on the table. So I'm going to go over here and put 0.626. I'm going to go down here to the 3 and put 0.626. And, oh no, 0.292 is not on the table. That's because it's not real. It's not a real resistor. It's representing the 0.5 and the 0.7. But that's okay, I can still use it. Now, notice, the 0.5 and the 0.7 are in parallel with one another. And so, remember, in parallel, what stays constant? Voltage. And so if I know the total voltage drop across that pair, I know the voltage across the left half and the voltage across the right half. Because the thing is, that current by itself is not really important. I know that 0.626 amps is going to pass through the whole thing, but some of it's going to split and go across the left side, some of it's going to split and go across the right side. But if I know the voltage, I can find out exactly how much that is. So if I know ohms and I know amps, I'm going to multiply them together. Why? Well, remember, V equals I times R. So if I know I and I know R, multiply them together. And I get a voltage of something. 0.183. 0.183 volts, and that'll show up in a second, hopefully. There it is, 0.183 volts. Now remember, that's the drop across this pair, 0.5 and 0.7, but because they're in parallel, I'm going to have 0.183 volts here, 0.183 volts here. Are they both real resistors at this point? Yes, they are. So I'm going to add that information to my table. So I'll go over here to the table, and I'm going to add 0.183 volts for that one. There was the quarry that just did an explosion, and it shook everything. 0.183 in both of those. And once again, guys, if you got 2 out of 3, you are good to go. So now you can just start plugging and chugging using, again, this relationship at the top of the table. V equals I times R. So 0.626 times 1.5, I get 0.939. 0.626 times 3, I get 1.878. And then for these next two, I'm not going to be multiplying, I'm going to be dividing. So I'm going to do 0.183 divided by 0.5. I get 0.366. Sorry, that was some bad handwriting. Let me try that again. Always do leading zeros, guys. Don't forget, put a 0.366. Otherwise, it might look like 366. Last one, I'm going to do 0.183 divided by 0.7. And so I get 0.261. So there you go. There are checks that you can do for this one. For instance, if you add together 0.366 right here, let me just show you. 0.366, 0.261, if you add the two of those together, what do you know? It equals 0.626, which is the same value we had over here. Okay, look over there. And so it does work. You can also add all your voltage drops together, so that 0.183 plus the voltage drop across your other ones in series, so that'd be this 0.939 value, and that would also be this 1.878. Hey, what do you know? That equals 3. That's the total voltage across the battery. So there are some checks you can do, but you've got to be really smart about it. You've got to really think about what you're doing. I'm gonna teach you another trick tomorrow that is very important. That tells you about a fourth column on the table. That is just, it is literally magic. You guys are gonna love it, but not today. All right, let's look at the next one, number 4. The next and last one, problem number 4, and it is a beast, but I love it. Love this problem. Once again, I want to start by filling out my table, and so I will do that. Let's see, I've got a 1 ohm resistor, a 3 ohm, another 3 ohm, a 7 ohm, a 2 ohm, and a 4 ohm. Now be careful. In fact, I'm going to put some brackets next to this 3 and this 7 so that we know which ones I'm talking about. I'm talking about the two that are matched together. That was kind of, I don't know, I probably shouldn't have done that. I should have made that 5 or something. But anyway, it's all right. Help keep you on your toes. All right, so in this circuit, once again, I am going to look for the most specific part of this circuit, and that's going to be the 3 and the 7, okay? Because think about it. They're in series with one another. By the way, I'm talking about these right here. They're in series with one another. They're in parallel with 3, but that whole group together is in series with 1, and that whole group together is in series with the 2 and the 4. So this is the most complex part. Because these are in series with one another, 3 and 7, I just simply add them together and I get 10.0 ohms. At this point, I'm going to do this whole section right here. Boy, that was a pretty circle. Because now what we can say is the 10 and the 3 are in parallel with one another. How do we combine resistances in parallel? With that really annoying equation that you guys probably don't like. So I've got 1 over 3 plus 1 over 10, right? And I'm going to invert that. So I'm going to do that to the -1 power after I do it in my calculator. In fact, I'm going to do that right now. Once again, I know I've said it before, you guys should be doing this too. Do not trust that I do it correctly. You make sure you know how to get it in your calculator. I get 2.31. Hope that's what you got at home. So I get 2.31 ohms for this whole group. Let's go ahead and take a look at this bottom section down here, the 2 and the 4. Same thing. The 2 is in parallel with the 4 ohm resistor. So once again, I have to do that annoying equation. 1 over 2. Let's make that a little prettier. That looks terrible. 1 over 2 ohms plus 1 over 4 ohms. And I'm going to then invert it in my calculator. Let me do that real quick. Again, you check. So literally what I'm typing into my calculator right now is parentheses 1 over 2, close parentheses, plus open parentheses 1 over 4, close parentheses, and then I hit enter, and I get 0.75. And then without touching anything, I do the x to the -1 button, and that inverts it for me. So I get 1.33. Not watermelons, 1.33 ohms. Always make sure you put the unit next to it so you don't get confused, because there's a lot of numbers we're playing with right now. So let's pause for a second and recap. Let's talk about what we just did. I took a very complicated circuit, okay, which we got a 10.0 volt battery that's in series with a 1 ohm resistor. But now what I've done is I've simplified it quite a bit. Because at this point, I can say, oh, well, I have a 2.31 ohm resistor. I'm going to put that in quotation marks because it's not real. And that's in series with this other imaginary 1.33 ohm resistor, right? That's down here at the bottom section. And they're both in series with the 1 ohm resistor and with the battery. So at this point, then, finding REQ is pretty easy because you just use addition. Okay, so let me erase this, get cleaned up a little bit, and we'll get started. I'll tell you what, I'm gonna do it over here on the right where I've got a little more room. So I'm gonna find REQ of the whole circuit. There we go. So I'm gonna say, all right, well, REQ is equal to the 1 ohm resistor. Keep in mind the 1 ohm resistor is actually a real resistor, plus this 2.31 ohm resistor, plus finally, before I slightly run out of space, there we go, the 1.33 ohm resistor from the bottom. And again, those last two are fake, but we still need to use it to find REQ. And so I get some numbers. All right, I'm just going to add this up. They're all in series. That's why we're not using the annoying equation. When they're in series with one another, you just add them up, and I get 4.64 ohms. Ooh, that was a nice omega. Here, I'm going to make a pretty one. Not really. Okay, so at this point, what's the significance of that number? What I did is I took the battery and made it in series with a single resistor. So every other resistor is wrapped up in this fake 4.64 ohm resistor. Why does that matter? Well, now I can use REQ. I'm sorry, V equals IR. Not just any VIR, the totals and the EQ. Because I need to find current. I really need current. So what I'll do is I've got a 10.0 volt battery. I'm looking for I total, so I'll just leave it like that. REQ for the whole circuit is 4.64 ohms, which is what we just found. And I'm going to do some math. So in my calculator, you guys know how order of operations works, or you hopefully know how to do algebra if you're in physics. And I get 2.16. 2.16 amps, because that is a current amount. And that'll load in a second. There it goes, just thinking about it. Okay, so 2.16 amps. And guys, just like I've told you before, that represents the current through the battery. So what I'm going to do is I'm going to write it over there just to make sure I understand that. And so what that means is that's 2.16 amps through everything that's in series with the battery. So that means this 1 ohm resistor has 2.16 amps through it. Remember, in series, current through the battery is current through everything. It's equal. So that's 2.16 amps through that. That's 2.16 amps through this imaginary 2.31 ohm resistor. And that's 2.16 amps through this bottom section, the 1.33 ohm resistor. So at this point, okay, did I put that on any real resistors? Yes, I did. in the top left, I did it for the 1 ohm resistor. And because that's real, I can add that in the table. So I'll go ahead and put 2.16 amps right there. That's good. But now I'm looking at this red section. All right, I have 2.16 amps. I have 2.31 ohms. But that doesn't really tell me a lot. I know 2.16, part of it's going to go in the top section and go through the 3 ohm. Part of it's going to go through the bottom section, the 3 and the 7, but I don't know how much. But what I do know is that in parallel, voltage is constant. So if I can find the voltage drop across that whole 2.31 section, I know the voltage through each individually. So V equals IR tells me, in case you've forgotten, here it is again, V equals I times R tells me if I do 2.31 times 2.16, I get 4.99 volts. Guess I'll use this. So I get 4.99 volts. All right? And because it's in parallel, that means that's 4.99 volts here, and that means 4.99 volts through the bottom section. And I'm sorry that's kind of small, guys. We got a lot of information going on, but I hope you see what I'm adding. So I added 4.99 across the top, 4.99 across the bottom, because that's the rule in parallel. Voltage is constant. And notice, the 3 ohm resistor on top is a real resistor. That's actually a real resistor. So I'll add 4.99 to the table. Make sure that you're adding it next to the correct 3 ohm resistor. Okay, let me zoom in a bit, guys. We can do better than that. So here's what we're doing now. Now that I know I have 4.99 volts across that bottom section, let's go ahead and finish that up. 4.99 volts, not really helpful here, okay, because I can't put that on the table for anything. I know that 4.99, part of the voltage drop or the pressure difference is going to occur across the 3 ohm, and I know the other part of that voltage drop is going to occur over the 7 volt, and they're going to add up to 4.99. But because these are in series, what stays constant in series? Current. So if I can find current, I can find the current through each of them because it'll be the same. Now, V equals IR tells me, and in case you've forgotten, I'll write it over here in the way for a second. I know it's V equals I times R, but if I'm looking for I, it's going to be V divided by R. All right, so be careful about that. Make sure you're doing what you should. So I'll do 4.99 volts, and then I'm going to actually divide it by 10.0 ohms, and that's going to give me my current. So 4.99, I'm not sure why I'm putting that in my calculator. That's just 0.499. But now that I know the current is 0.4999 through that whole bottom branch, I know that it's going to be 0.499 through this one, and 0.499 through this one. Make sure you use that decimal. Don't get confused. And guys, the 3 and the 7 are real resistors. So I can put that 0.499 value here and here. And again, I was able to do that because of the rule for current in series. I in series is constant. And so if it's 0.499 through the whole bottom branch, it's the same thing through each of them. Let's take a look at this bottom section and wrap this thing up. So down here, I know 2.16 amps is going through this pair, the 2 and the 4. But I know that 2.16 is going to split. Some of it's going to go through the top, some of it's going through the bottom. But what's constant in parallel? Voltage. And so once again, because I know Ohm's law is V equals I times R, hey, I have I and R. How helpful is that? So I'll go in, multiply these two together. So I'll do 1.33 times 2.16, and I get 2.87. 2.87 what, guys? If I did current times resistance, you better believe this is going to be voltage. So 2.87 volts. And so what does that mean? That means I have 2.87 volts here, 2.87 volts here. Because if they're in parallel, the voltage drop across the whole thing, the pressure difference across the whole thing, the color drop or color coding across the whole thing is going to be the same through each branch. And 2 and 4 are both real resistors. So I can put 2.87 in the bank over here on the table. And at this point, if we take a look at our table, we have 2 out of 3 for everything. So now what I'm going to do is I'm going to use some math and fill out the rest of the table. 2.16, and I'll show you guys, look, 2.16 times, these are times, these are times. This 4.99 is going to be divided by 3.0. 2.87 divided by 2.0, divided by that. Make sure you know what you're doing and why based on Ohm's law. V equals I times R. So 2.16 times 1, it's going to give me a very surprising 2.16. 4.99 divided by 3 is going to be 1.66. 3 times 0.499 is 1.497. 0.499 times 7 gives me 3.493. And honestly, I'm probably using more decimals here than I really need to. I'm going to the thousandths place. Typically, I think we stop at the hundredths, but it helps you with your exactness. It helps make sure that when you check yourself, okay, using one of the tricks that I've taught you, when you check yourself, it makes it so that the numbers are a lot closer. And you don't have to scratch your head and be like, oh, does 4.99 mean 5? I mean, usually. 2.87 divided by 4 gives me 0.718. Let's call it 718. And so, guys, I could go through and show you all the checks. I don't think I'm going to. I think that would confuse you. Just trust me. Tomorrow, Thursday, on October the 22nd, I'm going to teach you about power. And that is going to give you the power to check these a lot more easily. Guys, it's important that you understand how to do these problems. It is kind of like a puzzle. I think that's why I enjoy it. But you've got to be able to think through and say, all right, if these are in series, what stays constant? Current. If these are in parallel, what stays constant? Voltage. Like, you've got to be able to think through it, and I hope you did that. If you guys have questions, you know how to get in touch with me. Thank you for your time. I hope you enjoyed this recording.